Hello everyone, so it's just a quick discussion to come back on various claims that are being made on the interwebs having to do with um, true and correct statements of the first law or maybe even the second law of thermodynamics. The only thing I would like to put forward here is really that this is not as straightforward as one might think. And one of the reasons for that is that it's really difficult to trace back which one is a reference that we should use to say, okay, this is the thing we need to look at to determine whether this particular statement of the first law is correct, or this particular statement of the second law is the right one. And what I would like to highlight as well, and this is something I've repeated quite a few times on my small channel, which is that essentially the fact that there is one, for example, particular formulation or statement which is going, let's say, to be retained or remembered by many people in expert disciplines such as like chemistry, physics, engineering, and so on, does not mean that this one was the real statement of the first law or the second law or anything like that. Okay, so as soon as a particular formulation simply has the ability to, let's say, propagate in higher education institutions, then automatically, by default, this is what all the future experts are going to learn. And so this is going to induce, if you will, a consensus among experts about what these laws are going to be. But this consensus is not grounded in introspection, reflection, and critical thinking. It's grounded in what you've been told in your education. And I do fall as well, obviously, in the same category. I'm prone to the same things as well. I've been taught certain things, and there are some of them maybe that I don't put into question or don't try to go back to the original sources. So here I just wanted to point out, because again this is discussed in many areas these days. This is a paper that was published in 1958, so you see, quite some time ago, and that was about statements. And please notice here that there is an S of the first and second laws of thermodynamics. So 58, you could say that this is about 100 years after the inception of thermodynamics, kind of roughly speaking. So let's see what these people had to say. So first of all, I'm not going to go obviously through the entire paper. I'm going to put a link in the description to the actual paper if you want to have a closer look at it. But the interesting part is this one here, for example. So you see, this is about the second law. So what the person says here is that there have been nearly as many formulations of the second law as there have been discussions of it. And in fact, what they say just after that is the first law also is expressed in many different forms, implying here that essentially these different forms need not be equivalent in any standard kind of sense of the word. So here there is basically an idea about what is the main ground kind of idea around the first law of thermodynamics, which is around the concepts of energy and conservation. The idea being to somehow promote an extended version of what is called conservation of mechanical energy, which had been proposed in the development of, for example, analytical mechanics in the 19th century and early 20th century. So that's the kind of things that was put forward. But the thing is, there are various discussions here, but really trying to mention some notion about heat as being related to the notion of conservation of caloric or the caloric fluid. So that's where the word calorie comes from. It's supposed to initially evaluate the amount of caloric fluid which has been transported from one particular material onto another. But the thing here is that I think we can have a quick look at this here. So there are 4 categories of statements, okay, so multiple statements are being made here, and the authors are able to classify them into 4 categories. So essentially there would be statements of the first law, which are about, which concern the impossibility of perpetual motion of the first kind. So there are multiple kinds of perpetual motion. So the first law of thermodynamics would concern the impossibility of perpetual motion of the first kind, and the second law of thermodynamics would actually concern the impossibility of perpetual motion of the second kind. So you may want to look at these terms on your own if you want. There is plenty of documentation available, for example, on Wiki. So then you've got another kind of statement, which is statements concerning the mechanical equivalent of heat. So here the idea is to say that, for example, if you try to do work adiabatically onto a system, you're going to observe a similar effect to what you would observe without doing any work, but by providing heat, for example. And likewise, if you do a heat transfer onto a particular material, this material can exert work onto something else as well. Then you've got statements concerning energy conservation, so that's something really very broad and very large, and then statements concerning internal energy as well. Okay? So the thing here is that these authors subdivide this into various categories of statements that are being found in various textbooks. So here, these are verbatim what is found in textbooks from the different references they've looked at. The references they've looked at go back to, I believe, 1908 with a work from pointing. So if people know electromagnetism, there is something called the pointing vector. So there's the same pointing person. So that's basically the kind of things being looked at. So there is one that I can't read, so maybe some of you can put, if you read German, tell me what this one says. I will put it later anyway in Google Translate, but for the time being, I'm actually unable to understand this one. But the thing is that the first statement is that it is impossible to construct a machine which shall produce no other effect than the generation or destruction of mechanical work or of any other form of energy. Okay, so it's impossible to construct a machine which will produce no other effect than the generation or destruction of mechanical work or of any other form of energy. So that's the idea, and I think here the point is to imagine a machine which has to work in cycle. Okay. Then the second one again, I can't, I don't understand what is written there. So unfortunately, we have to leave it there for now. The second one, let's see, maybe I can try to increase a bit the font size. So heat is a form of energy. Then energy is conserved. And energy is conserved if heat is taken into account. So the idea here is just to really expand the notion of energy. So we add to the notion of mechanical energy just the fact that there is heat on top of that. And so as soon as we've provided that, we say, well, if we add heat to anything else, essentially we are going to get the first law of thermodynamics. And then there are statements which introduce a new concept, which is that of internal energy. So in that case, essentially there is this one, for example, which is related to the viewpoint of the heat process. So if a system is caused to change from an initial state to a final state by adiabatic means only, the work done is the same for all adiabatic paths connecting the two states. Okay, so that's really important. It basically says that the work, essentially for adiabatic processes, becomes so it means that essentially there can't be any kind of dissipation stuff, otherwise it wouldn't be adiabatic. And so what that means is that essentially the work becomes a so-called function of state in that case. And then they say if the process is not adiabatic, then the heat involved dQ is defined by this. Now this du concern the variation in the quantity called internal energy, but this internal energy is not known kind of, experimentally. So this is something that you would have to figure out. If you express this equation in that fashion, you would have to know what is the, what you consider to be the internal energy of your system. If a system changes from some initial state to a final state, and if dq and dw are respectively the net quantities of heat absorbed and work done by the system during the process, then we define the increase in internal energy du of the system during the process by the equation du equals dq minus dw. Okay? And by the way, note here that none of these statements involve notion of the system being so-called closed. Okay, so that's actually quite interesting. Many of these references were taken from books that were obviously 1958, but basically some of them from the 1940s and 1930s. So that's quite interesting as well. And then here there's a final one. The increase in energy of a system du, which occurs in any selected time interval, is equated to the net sum of quantities of energy dem carried into the system by transfer of matter, plus the net sum of quantities of energy dqn carried in by the transfer of heat, minus the network dw, etc. These summations here, they need to be interpreted as being what we would write nowadays as integrals. Okay, so they are summations of infinitesimal kind of changes. So basically that's it. So you see that there are very, very different statements that are being made. And they are not necessarily here specifying which one we should look at. They are just trying to say how these statements are going to focus on different aspects of thermodynamics and what they want to convey in terms of what is the ground principle of the first law of thermodynamics, what is captured really by it. And so there is a focus which is more kind of thermodynamical, and some of those that are a bit more just a generalization of what we would used to have from mechanics with, again, conservation of mechanical energy. Now, very quickly, we can have a look at the second law, just to say as well that there are many different statements that have been put forward. And I'm just going here to scroll through very quickly these different categories. So what they say here is that there is a statement, a class of statements concerning the conversion of thermal energy into work. That would be, for example, I think the Kelvin-Planck statement would fall in that category. The Kelvin-Planck statement fall in this one, statements concerning with the flow of heat between bodies at different temperatures. Statements concerned with the thermodynamic characteristic of all real processes, so that's something much broader, and statements of basically A and C expressed as thermodynamic functions. So there is also a mathematical characterization, so basically whether or not essentially the second law would claim that there is a so-called function of state, which is the entropy function, and so on. So basically that's it. And if you want to look more carefully, it's much more complicated for the second law. So there are plenty of different statements which are being considered, and you need to keep in mind that these are classes of statements. So they are already categorized, even in this table. They are actually categorized already, and there are many different kind of statements of that kind each time. Okay, so essentially there used to be as many statements of thermodynamics, almost as many as the number of people working on it. And I think this is something to keep in mind when one may, let's say, claim that one particular statement is this one, and then there is no discussion or debate about it. I think that would be quite disingenuous when knowing the actual history of the topic and the fact that essentially people never agreed, because even in 1958 people were still trying to work out what these different statements were saying, which ones maybe could be chosen by various people in essentially in the community of practice within thermodynamicians. So the idea here would be that the thermodynamician would know what they are doing, and essentially would express maybe sometimes things in terms of equations, but these equations would have some interpretative value, which would come with the practice itself. So that's kind of the idea. At the end, actually, they propose even that it should be split into 3 laws of thermodynamics instead of 2. So the principle of energy conservation, the principle of temperature as the potential of heat, and the creatability of its conjugate quantity, the entropy. So here, this is a mathematical notion again. And then the principle of creation of entropy as a characteristic of all real processes. So that, again, I'm just going to leave you there. This particular third law of thermodynamics usually is a secondary part, or sometimes the first one, depending on how you present it, of the actual second law in most textbooks. But the point here is that essentially it's very, very difficult to narrow down who you should look at, or which reference you should kind of look at if you want to know which law of thermodynamics to trust. Now, is that an alarming state of affairs? I don't think this is necessarily the case, because you can use the laws of thermodynamics to obviously emit some predictions and stuff like that. You can also use it as an interpretative filter, and so what that means that you're going to use these laws as a means to explain various things happening in the world as well. So that's kind of the point. So it's not the end of the world. Many actually amendments to the laws of thermodynamics, even the modern ones, have been proposed and are still being proposed today. And so that's how science should be, right? So things should be discussed, things should be debated, and then people should use the versions that they believe they use based on their critical assessment of the literature, critical assessment of the different arguments pro and for different versions of these laws, and then move forward with what they believe is right. So on these notes, I'm going to leave you there. I hope some of you are going to try to read this one, because I think it's a very interesting and very enlightening paper indeed. And otherwise, I will see you in some later discussion video.